Venus and Earth are twins, same size, same mass, same composition, formed at the same time from the same cloud of gas and dust, just a few 100 million kilometers apart. Today, Earth has oceans, forests, and 8 billion people. Venus has a surface temperature of 465 degrees Celsius, an atmospheric pressure 92 times greater than Earth's, enough to crush a nuclear submarine, and clouds made entirely of sulfuric acid. We share the same origin. We ended up in completely different universes. And here's the part that should make you very uncomfortable. We don't fully understand how Venus got this bad, which means we don't fully understand whether Earth could follow the same path. By the end of this video, I'll tell you about a discovery made in 2020 that split the scientific community in half and still hasn't been resolved. A discovery that forced us to ask whether we have been completely wrong about what Venus is. Let's go. Venus and Earth are twins, same size, same mass, same composition, same origin story, formed from the same cloud of gas and dust, in the same neighborhood of the early solar system, roughly 4.5 billion years ago. On paper, they should be nearly identical. They are not. Earth has liquid oceans, a breathable atmosphere, a temperature range where water stays liquid, 8 billion living things clinging to its surface. Venus has a surface temperature of 465 degrees Celsius, day and night, at the poles and at the equator, always. Its atmospheric pressure is 92 times greater than Earth's. If you stood on the surface of Venus without a suit, you wouldn't burn to death first. You'd be crushed, like a submarine diving 20 times too deep. Its clouds, the thick, brilliant white clouds that make Venus the brightest object in our night sky after the moon, are made of sulfuric acid droplets. They don't produce rain. They produce acid that evaporates before it hits the surface, and Venus rotates backwards. Compared to every other planet in the solar system, its spin is reversed, and it rotates so slowly that a single Venusian day is longer than a Venusian year. This is Earth's twin, and we still don't completely understand how it got this way. That's what we're here for today. Because the answer, or the attempt at an answer, is one of the most important stories in planetary science. And it has implications that go far beyond Venus. Stay with me, because this gets genuinely unsettling. Nobody had ever seen the surface of Venus until 1975. Because you can't, not from space, not with optical telescopes. The cloud layers are permanent and completely opaque. Venus hides its surface behind an unbroken ceiling of acid cloud that extends from about 45 to 70 kilometers altitude. The only way to know what's underneath is to go there. The Soviet Union tried, repeatedly. Between 1970 and 1985, they sent a series of landers called Venera to the surface of Venus. This was one of the most extraordinary engineering achievements of the space race, and one of the least talked about. The problem was simple and almost insurmountable. The surface of Venus destroys everything. The first landers were crushed by the pressure before they could transmit a single image. The engineers went back, redesigned, added more shielding, more insulation, made the spacecraft look like pressure vessels, because that's essentially what they were. Venera 9 and Venera 10, landing in 1975, finally survived long enough to send back photographs. The first photographs ever taken from the surface of another planet in our solar system beyond the Moon. Not Mars, Venus. The Soviets got there first, and what they showed was not what anyone expected, not a smooth, molten, featureless hell. Instead, rocks, jagged, angular rocks, geological features, terrain that looked, in some ways, disturbingly geological, almost familiar, except bathed in an orange glow from the thick atmosphere filtering the sunlight above. The landers lasted between 23 minutes and 2 hours before the heat destroyed their electronics. Today, the best maps of Venus's surface come from radar. The Magellan spacecraft, orbiting in the 1990s, used radar to pierce the clouds and map 98% of the surface at 100-meter resolution. What it found was a world dominated by volcanism, vast volcanic plains covering most of the surface, thousands of volcanoes, more volcanoes than any other planet in the solar system, a handful of highland regions that may be ancient continental remnants, and almost no impact craters, which tells us the surface is geologically young. Something resurfaced the entire planet within the last 300 to 500 million years. Something enormous happened, and we think we know what it was. Here's the thing about Venus that most people don't know. It may not have always been hell. In 2016, a team of scientists at NASA's Goddard Institute for Space Studies ran climate simulations of early Venus. What they found was striking. For potentially 2 to 3 billion years, a window that includes the period when life first appeared on Earth, Venus may have had a temperate climate, liquid water, oceans, a habitable surface. Let me say that again. Venus may have been habitable for longer than Earth has existed as a planet. The simulation depended on several assumptions. A slower initial rotation, which Venus may have had before tidal interactions with the Sun, gradually changed its spin, a shallow ocean covering much of the surface, and the younger, dimmer Sun providing less energy than it does today. Under those conditions, the model showed stable temperatures, a water cycle, a climate that, while different from Earth's, was within the range where liquid water could persist. Is this confirmed? No, it's a model, and models are only as good as their inputs. But here's what makes it plausible. We know that Venus has water, locked into its atmosphere as trace amounts of water vapor, and recorded in the chemistry of its rocks as evidence of past water activity. The ratio of deuterium to ordinary hydrogen in Venus's atmosphere is 150 times higher than on Earth. That ratio is a fingerprint. It tells us that Venus once had vastly more water than it does today. Water that has since been lost. Something took it. And here's where the story gets tragic. Because it wasn't a catastrophic impact that destroyed Venus. It wasn't a sudden event. It was physics. Slow, inevitable, unstoppable physics. And it has a name, the runaway greenhouse effect. The runaway greenhouse effect is not a metaphor. It's a specific, well-defined physical process. And it's the most terrifying thing I know of in planetary science. Here's how it works. Venus starts with liquid water oceans. Sunlight hits the surface. Some of it is absorbed, some reflected. The planet warms. As it warms, water evaporates. Water vapor enters the atmosphere. And water vapor is a greenhouse gas. It traps heat. So the atmosphere warms more, which evaporates more water, which traps more heat. This feedback loop, once it starts, has no natural break. On Earth, the carbon silicate cycle acts as a thermostat. When temperatures rise, silicate rocks weather faster, absorbing CO2 from the atmosphere, cooling the planet. A self-correcting system, imperfect, slow, but real. Venus lost that thermostat. As temperatures rose and oceans began evaporating, the weathering cycle couldn't keep up. CO2, released by volcanoes, no longer absorbed by liquid water and rock, began accumulating in the atmosphere. More greenhouse gas, more heat, more evaporation. The feedback loop ran away, completely. The oceans boiled, not quickly. This took tens or hundreds of millions of years. But they boiled. The water vapor rose into the upper atmosphere, where ultraviolet radiation from the sun broke the water molecules apart. The hydrogen escaped to space. The oxygen combined with surface rocks or was swept away. The ocean simply ceased to exist. What remained was a thick, dense CO2-dominated atmosphere. 96.5% carbon dioxide, 3.5% nitrogen, almost nothing else. That atmosphere creates the greenhouse effect we measure today, the 465-degree surface, the pressure that would crush a submarine. Venus didn't have a sudden catastrophe. It had a slow, self-amplifying disaster. And here's why this should concern you. The fundamental mechanism, rising temperatures increasing water vapor, which increases temperature, is the same feedback loop that climate scientists monitor on Earth. We have not triggered a runaway greenhouse on Earth. Our situation is categorically different. Earth is further from the sun, has more efficient cooling mechanisms, and has the carbon silicate cycle functioning well. But Venus tells us the feedback loop is real. It's not theoretical. It happened. That's not a reason for panic. It's a reason to understand it. And it's why studying Venus, understanding exactly how and when this tipping point was crossed, is arguably the most practically important thing we can do in planetary science right now. For decades, scientists suspected Venus might still be volcanically active. The surface is young, too young for a geologically dead planet. The atmosphere is constantly being resupplied with sulfur dioxide, a volcanic gas, in amounts that can't be explained by the existing atmospheric chemistry alone. But suspicion isn't evidence. In March 2023, a study published in Science provided the evidence. Researchers re-examined archival radar images from the Magellan spacecraft, images taken over 30 years ago, sitting in NASA's data archives. They compared images of the same volcanic region taken 8 months apart in 1990 and 1991. In that 8-month window, a volcanic vent had changed shape, expanded, grown. On Earth, that kind of rapid morphological change in a volcanic vent has one explanation: activity, eruption, lava, heat. Venus is volcanically active, right now, today, as we speak. This isn't a minor update. It means Venus has an active geological cycle, active volcanism, heat coming from the interior, a planet that isn't simply a dead relic, but a living, geologically functioning world hidden under those clouds. And it changes the picture of the atmosphere, because active volcanoes release not just sulfur dioxide, they release water vapor, carbon monoxide, hydrogen sulfide, complex chemistry that interacts with the sulfuric acid cloud layers in ways we don't fully understand. It means the Venusian atmosphere is more dynamic, more chemically complex, and potentially more interesting than we thought. It also means that whatever killed Venus, the runaway greenhouse event, didn't kill its interior. The engine is still running, and that engine creates chemistry. And chemistry, in the right conditions, can create something else entirely. Which brings us to the discovery that split the scientific world. In September 2020, a team of astronomers led by Jane Greaves at Cardiff University announced something that made headlines around the world. They had detected phosphine in the atmosphere of Venus. Phosphine, pH 3, a molecule of phosphorus bonded to 3 hydrogen atoms. On Earth, phosphine is produced in 2 ways: industrial chemical processes and biological processes, specifically by anaerobic microorganisms. microbes that live without oxygen. In the atmosphere of Venus, there is no obvious non-biological chemistry that should produce phosphine in the concentrations detected. The sulfuric acid clouds destroy it. The UV radiation breaks it down. Whatever is producing it must be producing it continuously, in significant quantities. The paper suggested a remarkable possibility: microbial life, floating in the cloud layers of Venus. At altitudes between 48 and 60 kilometers, where temperatures and pressures are remarkably close to those at Earth's surface. Around 30 degrees Celsius, 1 atmosphere of pressure. The most habitable zone on Venus isn't the surface, it's 50 kilometers above it. This sent the scientific community into immediate, productive chaos. Some researchers tried to reproduce the detection and couldn't find phosphine at the concentrations originally reported. The original data was reanalyzed. The signal, some argued, was weaker than initially claimed, or possibly an artifact of the instrument. Others proposed non-biological explanations: unusual volcanic chemistry, photochemical reactions involving sulfur compounds, processes we hadn't considered. The debate has not been resolved. What everyone agrees on is this: we cannot currently explain the full atmospheric chemistry of Venus. There are things happening in those clouds that our models don't account for. Whether those things involve biology or exotic chemistry, we don't know. And we won't know until we go back, really go back, with instruments designed specifically to look for biosignatures. In the cloud layer, where the conditions are actually, genuinely survivable. Tell me in the comments, do you think there's life in the clouds of Venus? Because this question deserves to be asked out loud. Before 2032, 2 missions will change everything we know about Venus. DAVINCI, deep atmosphere. Venus investigation of noble gases, chemistry and imaging. A NASA mission that will drop an instrumented probe through Venus's atmosphere, measuring its chemistry layer by layer, and then image the surface of a Venusian highland region called Alpha Regio in detail never seen before. DAVINCI will tell us definitively whether Venus once had oceans. The noble gas ratios and isotopic signatures in the deep atmosphere are preserved records of the planet's history, like reading tree rings, but for an entire planet. And VERITAS, Venus emissivity, radio science, INSAR, topography and spectroscopy, an orbital mapping mission that will produce topographic and compositional maps of Venus at a resolution 10 times better than Magellan. With VERITAS, we'll be able to see individual geological features, identify which volcanoes are currently active, map the distribution of minerals that would tell us where water once existed, and perhaps find the remnants of ancient shorelines, if they exist. These 2 missions together represent the most comprehensive Venus exploration since the Soviet Venera program ended in 1985. 40 years of waiting, ending before 2032. And here's why this matters beyond pure science. Venus is not just a fascinating dead world, it's a data point. The most important data point we have for understanding the limits of planetary habitability. We know of 3 rocky planets in the inner solar system with roughly similar compositions and sizes: Venus, Earth, and Mars. Mars lost its magnetic field and its atmosphere and went cold. Venus triggered a runaway greenhouse and went hot. Earth sits in between, and we still don't know precisely how wide that window is. Venus tells us the hot edge of the window. Understanding exactly when and why Venus crossed that edge, what the tipping point was, whether it was inevitable, or whether a slightly different set of initial conditions could have saved it, is directly relevant to understanding the long-term stability of Earth's climate. Not in a scaremongering way. Earth is not Venus. The differences are real and significant. But Venus tells us that planets can go wrong, that the conditions for life are not automatically self-sustaining, that a world can transform from habitable to hellish through processes that are, in principle, measurable and understandable, which means they are, in principle, preventable. Venus is not a warning about tomorrow. It's a lesson about physics, about what happens when feedbacks run away, about the conditions that make a world livable, and what can take them away. If you want to understand Earth's future, start by understanding Earth's twin. Subscribe, hit the bell, and let me know in the comments, which planet do you want us to cover next? Because we're just getting started. Until the next mission.